Hi again, this is Greg Smith from the Department of Applied Science and the Neuroscience program at the College of William and Mary. And we're working on a example phase plane analysis problem that is closely related to some of the problems on problem set 5. We're given the XY phase plane and the null lines in red and blue is shown, and we were also given the direction of flow in one of the regions that are delimited by these null lines. And we figured out then by changing the x direction of flow from increasing to decreasing whenever we cross the x null line, and changing the y direction of flow from increasing to decreasing whenever we cross the y null line, we figured out the general direction that solutions would be moving in each of these areas. Now, often we'll know that the dynamics of one of our variables in our two-dimensional nonlinear ODE system is much faster than the other. So and most of the time, the fast variable will be on the horizontal axis, so that's more of a convention than a necessity. But in this case, if we know that x is a fast variable and y is a slow variable, that means that if we're not on or near an x null line, the flow is going to need to be essentially horizontal, because if x is changing quickly and y is not changing much, that means we're either moving left to right or right to left. So the rule is going to be that trajectories will be essentially horizontal, close to horizontal, whenever the state of the system is not near an x null line. So, for example, if we wanted to ask what would happen to a solution that began at this location. So if this was the initial condition for our nonlinear ODE, we could ask what direction would it go? How would the state of the system evolve as time moved forward? And one thing that we notice is that at this location, we're in a region of the phase plane where x is increasing and y is increasing. Now, x is a fast variable and y is slow, so we'll essentially move horizontally. We'll move towards the right because x needs to be increasing, and we'll drift up slightly because y is also increasing, but just slightly because x is much faster than y. So let me move like this. Now, when we get to the x null line, we're in a situation where we're being told that the rate of change of x is 0. So that means that we should think about the slower time scale and what happens to the dynamics of the slow variable when x is essentially is slowed down is moving very slowly, is close, the rate of change is close to 0. So what you can imagine happening is that y now changes, and that y would actually increase because this is a region of the phase plane where y is increasing. But whenever y increased a little bit, x is fast, and it will, since the flow of x is in the leftwards direction or decreasing here, we would be right back onto the x null line. So what happens is that the solution kind of meanders very close to the x null line, but it drifts upwards along the x null line because the rate of change of y is increasing in this region. And you can think about it as though the solution is trying to travel towards the y null line. The direction of flow in the y component of the direction of flow is moving towards the y null line. So I'm going to put some arrows on this just so we don't lose track of the direction that we're going. Now, as y increases and we stick on and we stay onto the x null line, eventually we'll get to this point where an increase in y leads to there being no more x null line. And when that happens, the solution will be in this region where x, we can see, is supposed to be decreasing, and x is supposed to be decreasing quite rapidly. That's also true in this region. And so what will happen when we get to this knee of the x null line is x will decrease rapidly and will drop all the way to this branch of the x null line. We know that we have to move quickly because if we're not on the x null line, the solution needs to be horizontal, essentially horizontal, and we know we move leftwards because the direction of flow in both of these regions is leftwards. And then a similar argument as we had before is that if we're going to be close to this x null line now, time will go by and we can ask what will happen with the slow variable. And in this region y, the slow variable is decreasing, and so we'll crawl slowly along the x null line in the downwards direction. And now let us ask what happens when we get to this point. Well, at this point, we're at an intersection of the null lines. Both x and y are not changing, and the solution, the trajectory will asymptotically approach that stable steady state. And so, beginning from this initial condition, with the knowledge that x is a fast variable and y is a slow variable, we can figure out that this is essentially the trajectory that the system will go through. And this solution curve is an excitability because we went on a long excursion and then came down to this rest point. Now let me do one more. I'm going to change the color of the pen to gray, and let's ask what happens if we start here. Okay, so if this were our initial condition, we're in a region where x is decreasing and y is increasing, but x is supposed to be changing faster than y when we're not on an x null line. So we would move to the left until we get to an x null line. Here, the flow in the x direction is reversing, right? On this side, x is increasing, and on this side is decreasing. So we'll stay on this stable branch of the x null line, and we will move in the direction of increasing y because y is increasing in these regions until we get to this point. And here, at this location, this steady state will stop. Notice that the flow in the x direction is towards the steady state, and the flow in the y direction is also towards the steady state. So it looks like that steady state is going to be stable. Let me see if I can do one more. How about a little green trajectory this time? Where should we start? How about let's start here. No, that's no good. That's going to be not a little uninteresting. Let me start here. Right now, x is the fast variable, and in this region x is decreasing, so we would drop to this x null line. Then in this region y is decreasing, so we would move down until we got to this steady state where we would stop. Okay, so not all initial conditions are going to lead to this a very long trajectory. So I think that's enough. I've just shown you how you can sketch several different trajectories on this phase plane using the knowledge of the general direction of flow for x and y, and also the fact that x is a fast variable and y is a slow variable. I hope this helped you on problem set 5, and talk to you soon.